We ended last week by talking about freezing point depression, and then we made ice cream, right? So boiling point elevation is extremely similar. The equation has the same form. What's different is that it has B's instead of F's, right? So delta T, B is the change in the boiling point, M again is the molality of the solution, and KB is the boiling point elevation constant. So here we have a picture of someone pouring antifreeze into their car radiator. And by adding antifreeze, which is often ethylene glycol, that causes the freezing point to lower and the boiling point to elevate. And so then your radiator can function and cool your engine over a wider range of temperatures, which is, a really good thing. So the boiling point elevation constants are on this same table as the freezing points, and here are the normal boiling points of these substances. So for water, it's 0.512. We're going to need that in this example. 0.512. So calculate the boiling point of a 3.60 molal aqueous sucrose solution. So we just looked up the boiling point elevation constant, 0.512 degrees Celsius per molal. The change in the boiling point is equal to the molality times that constant. So they gave us the molality, and we multiply by the constant. And then we get a calculator. And 1.8432 degrees Celsius. Important to remember, that is the change in the boiling point. The question's asking for the boiling point. And this is something that you should expect on a multiple choice exam. If this was a multiple choice exam, this would be one of the choices. Because the wrong answers are not random. The wrong answers are the answers that students get when they do common mistakes, right? That's why, students say, go, multiple choice, yes, it's easier. I don't think so, but whatever. So that's the change in the boiling point, right? And again, it might be most helpful to think about, a thermometer. And so this is water, right? And so it boils at 100, freezes at 0. And the boiling point goes up, the freezing point goes down. They move away from each other. So this is how much the boiling point increases, right? So the new boiling point then is 100 plus that, or 101.84 degrees Celsius. Any questions?
Does it always go up for solutions?
Yes, the boiling point always goes up, and the freezing point always goes down. And it's because of how the solute particles interfere with the process of melting and boiling. Yeah. Any other questions? Another colligative property is osmotic pressure. So osmosis is the flow of a solvent from a solution with a lower concentration to one of a higher concentration. And that's the process by which drinking seawater would cause dehydration, because it causes the water to move from the less concentrated salt solution in your cells to the more concentrated salt solution in your stomach or intestines. A semi-permeable membrane as the name suggests, is permeable to some things. So this is a membrane that allows some things to pass through, but not others. And biological cells have semi-permeable membranes. And so osmosis is an important process in biology. So this is what's called an osmosis cell. So we have this U-shaped tube. I used to call it a U-tube, but that's something else now. And it's got a little membrane here, a semi-permeable membrane. On one side we have pure water, and on one side we have a solution, salty water or sugar water or something. This has solute particles, this doesn't. So the semi-permeable membrane allows water molecules to pass, but it doesn't allow the solute molecules to pass because they're bigger. So initially the levels of the liquid are the same in both sides, which is exactly what we would expect if there was no membrane here, right? Because the water will go to the lowest point and the levels will be the same. What we see in this situation, though, is after some time occurs, the level of water on this side gets higher and the level of water on that side gets lower. The difference in those levels represents a pressure, okay? So that's called the osmotic pressure. What's happening here is with the osmosis, we're having water molecules move from the side that's less concentrated to the side that is more concentrated. And one way you can think about that is, well, the water molecules can move in both directions, but coming back, they're going to be somewhat blocked by solute molecules, and so going back is going to be at a lower rate than coming over in the first place. It's not the super most accurate way to think about it, but it's one of the easier ways. So what we call osmotic pressure is the amount of pressure that you would have to put on that thing to keep osmosis from happening. So looking at this again, so this difference in pressure is going to be very small because these are this is heights of water, not mercury. But in order to prevent this from happening, we would have to put some pressure here. Now, have you heard of reverse osmosis? We talk about water for purification things, right? For reverse osmosis. Well, reverse osmosis works by putting more than the osmotic pressure on this side and forcing the water into the less concentrated side, basically forcing the water through this membrane. That's reverse osmosis. So osmotic pressure has this equation. This is a capital pi. So the osmotic pressure is equal to the molarity times the ideal gas constant times the temperature in kelvins. This is molarity, not molality, because we're not talking about things changing temperature. We use molality for freezing point and boiling point changes because the temperature is changing. Here we're looking at one temperature, so we can stick with molarity. The ideal gas constant here, there's two different values that we've seen. This is the one with liters and atmospheres in it. And if we look at the units, so molarity would be in moles per liter. And this ideal gas constant is in liters times atmospheres divided by moles times Kelvin. And then the temperature is in kelvins. And so the moles cancel, the liters cancel, the kelvins cancel, and we're left with a pressure unit. So sometimes it's hard to know which of those two ideal gas constants am I supposed to use. The other one has different units. Joules per mole Kelvin. And there's a relationship between liter atmospheres and joules, but it's a lot easier to just use the one that has the more convenient units. So anytime you're doing something with energy, you want this one. But here we want the regular gas constant one. Calculate the osmotic pressure in atmospheres of a solution containing 1.50 grams of ethylene glycol in 50 milliliters of solution at 25 degrees Celsius. So the osmotic pressure is equal to the molarity times the gas constant times the temperature. So they didn't give us the molarity. They're going to make us calculate that. So our solute here is ethylene glycol. And so we need to convert that to moles using the molar mass. So 2 times 12.01 plus 6 times 1.008 plus 2 times 16. 62.068. Zero point 24167 moles. And then molarity is going to be the moles divided by the volume of the solution in liters. So if you're good at just moving the decimal point, you can do it that way, or you can write out the whole conversion, or you can do this. 50.0 milli stands for times 10 to the minus 3 liters. So I've got my moles divided by 50 times 10 to the minus 3, and I get a molarity of 0.48334. So hopefully at this point in the semester, that seems very doable, calculating molarity like that. So here's my molarity. And then I'm multiplying by my ideal gas constant, 0.08206 liters times atmospheres divided by moles times kelvins. And then I'm going to multiply by the temperature in kelvins. So 25 plus 273 gives me 298 Kelvin. And we see that our units are all going to cancel out nicely. And rounding to 3 sig figs, we get 11.8 atmospheres. Which is actually a large pressure, right? That's almost 12 times the pressure of the regular atmosphere. Any questions?